Hello everyone and welcome to the chapter of the hydrocarbons wherein we are going to take a look into the different reactivities with respect to alkenes. Now we already know that there are various type of hydrocarbons: aromatic, aliphatic, correct. In the aliphatic sections we prominently have three different classes. The particular class wherein we have carbon-carbon single bonds, what we call it as the alkanes. We have completed this entire section in the normal offline classes. While the particular compounds which contain carbon-carbon double bond, we call them as alkenes. While the third section lies with respect to those particular compounds which contain carbon-carbon triple bond in an aliphatic system, and those particular things we call it as an alkynes. Right? So alkanes, alkenes and alkynes. Triple bonded alkynes, double bonded alkenes, single bonded alkanes. Correct. Now we have completed majority of the reactions, but I would like to start from a particular checkpoint, and that is going to be the Markovnikov's rule. Okay, so here we are going to take a look into the first part of it, which is the reactivities of alkenes with hydrogen halides. Okay, so now when we say hydrogen halides, that means this is a compound which is going to contain hydrogen, right? And it is going to be connected to halogen. So HX. Now basically this means that you are going to take a look into a reaction which is going to be like an addition of hydrogen halide to a compound containing carbon-carbon double bonding, and so therefore we are going to look at the reactivity with alkenes. Okay, so now here there are certain things that we need to understand. That is, what is a type of alkene with which we are going to add this hydrogen halide. Okay, but before that we need to know the order of reactivity. Okay, so order of reactivities of hydrogen halide. Okay, so if we have different types of hydrogen halide, that is hydrogen chloride, hydrogen bromide, hydrogen iodide. Okay, now who is going to be more reactive and who is going to be less reactive? So therefore when we take a look into the order of reactivity, the most reactive among these are hydrogen iodide. Okay, so hydrogen iodide is going to be most reactive. Followed by what we have is the hydrogen bromide, and followed by we have the last one, hydrogen chloride. So this is the order of reactivity which we need to keep in our mind. Now we are going to take these particular hydrogen halides, which we are going to generally represent it as HX. Okay, so HX refers to these particular hydrogen halides. Now how do these hydrogen halides react with alkenes? So basically alkenes are of two types now. Okay, we can categorize these alkenes into two categories. One is, I can take over here with respect to a symmetrical alkene. Okay, so what we are taking here is symmetrical alkenes. That means these are the compounds wherein the neighboring atoms of a carbon-carbon double bonds are same. Okay, or similar you can say. So therefore, if we have a symmetry in these alkenes, for example, if I am going to take over here an ethene, okay, so this is an important example or a common example, as we can say, for a symmetrical alkene is concerned. Okay, now second type of an alkene which we can categorize is going to be the unsymmetrical one. Okay. So unsymmetrical alkene, right? So now you need to know that how these particular hydrogen halides are going to add up, or how they are going to react with symmetrical and unsymmetrical one. Unsymmetrical alkene, I will take an example such as propene. Okay, so this is propene over here. Okay, so observe carefully what is the condition around this carbon-carbon double bond. If I am just going to cut this particular molecule and the carbon-carbon double bonding, what is the condition? We do not have the same environment, correct, on the either sides of carbon-carbon double bond. So therefore, this one is an unsymmetrical. While if I am going to take over here and if I am going to cleave or if I am going to cut over here at the carbon-carbon double bonding, so what I am going to have on the other sides of carbon-carbon double bond, we have two hydrogens there, two hydrogens over here. So that is a symmetrical one. So now, first we shall discuss with respect to symmetrical alkenes. So when I take over here with respect to a symmetrical alkene, okay, and if we add any of the hydrogen halides, okay, so this addition of hydrogen halide over here, what is going to happen? One hydrogen over here, the hydrogen one we have, it is going to react or it is going to add up to one carbon of the carbon-carbon double bond. Okay, to any one of them. You can select any one of them. While the next one, as what we have over here, is the halogen, right? So halogen will be reacting with the another carbon of a carbon-carbon double bond. So quite simple. So if it is symmetrical, you can add a hydrogen wherever you want for this particular carbon-carbon double bond. Okay, and halogen you can add up to any of these particular carbons of a carbon-carbon double bond. This is a key point. So now here, once we have added, what is happening? Hydrogen is going to the first carbon over here. So I am going to get here CH3. Okay, single bond CH2. Alright, so this particular CH2 is going to be added up to this halogen. It is going to connect to the halogen. So this is what we are going to get. So in case if it is a symmetrical one, okay, it doesn't matter where you add hydrogen, it doesn't matter where you add the halogen for a symmetrical alkene. Okay, but those particular carbon-carbon of the double bonds there. Alright, so if I am going to take one example, let's say I am going to take the same ethene as an example. Okay, double bond over here, CH2, let's write the name, it is ethene, right? Two carbon systems. So plus, let's take this one with HBr. Quite simple. Now, what was the condition? Symmetrical. You can add hydrogen to whichever carbon you want for a carbon-carbon double bond. Okay, now let's say that I am going to add up this particular hydrogen over here to the first carbon. Alright, so if that is the case, then what I am going to get here? CH3. Okay, this is going to be CH3 for the first one. Now, let's say that we are going to have this bromine. The bromine is going to get attached to the second carbon over here. So what is going to happen over here? It is BrCH2. So this is going to be the answer. So it is bromoethane as an IUPAC name is concerned. Alright, so now we can also take one more example. Let's take one example such as CH3, CH, double bond, CH, CH3. Alright, so now if I'm going to add this one with, let's say, HCl. Okay, now again, it is a symmetrical one. Okay, if we take a look at the name of this is concerned, 1, 2, 3, 4. Alright, 4 means it is but. Okay, now it has a double bond E. But where is the position of the double bond? It is at the carbon number 2. So it becomes as but 2E. Right? Okay, now let's say that this particular hydrogen we are going to add it over here to the carbon of a carbon-carbon double bond. Okay, so if we do that, so CH3, CH2, this particular hydrogen has come over here, right? So this carbon has now two hydrogens which we have represented here. Okay, so now after this, alright, let's say this particular chlorine is going to get attached to this carbon of a carbon-carbon double bond. So therefore, we are going to have it as CHCl. And what we have is CH3, right? So this is how it becomes. So therefore, this particular section, as it has 1, 2, 3, 4 carbons, and at the position number 2, there is a chlorine. Okay, so numbering starts from 1, 2. So therefore, it becomes as a 2-chlorobutane. It is a single bond mix now. So therefore, this particular section becomes as 2-chlorobutane, right? So this is how it happens. So what is a key point to understand? The key point is, if you have a symmetrical alkene, addition of hydrogen iodide will give rise to only one type of product. Only one product you are going to obtain. That's it. Okay, and that is a key point which you have to remember, which you have to note it down. So addition of hydrogen iodide, hydrogen bromide or hydrogen chloride to symmetrical alkene will give you only one type of product. Done?